Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to just close your eyes for a second. Well, assuming you aren't driving or operating heavy machinery, right?
Yeah, please keep your eyes open if you're behind the wheel.
Exactly. But if you can, I want you to imagine that you are standing at the exact center of our galaxy, the Milky Way.
Which is an incredibly hostile place to imagine yourself, by the way.
Oh, it's terrifying. You aren't looking up at some peaceful, twinkling night sky from a quiet suburban backyard in the Orion Spur.
Right, not at all.
You are completely surrounded by an environment so dense and so utterly chaotic and violently dynamic that it practically defies human comprehension.
It really is like a cosmic mosh pit out there.
That's the perfect way to describe it. You've got millions of massive stars packed into a volume of space where, we might only see one or two stars around our own sun.
And if you had eyes that could see across the entire electromagnetic spectrum, the radiation would just be absolutely blinding.
Right. And the gravitational forces are pulling, twisting, and warping literally everything in sight. And right there, anchoring this entire terrifyingly beautiful merry-go-round, is Sagittarius A.
Our resident supermassive black hole.
Yeah, the one packing the mass of 4 million of our suns into a space that I think could easily fit inside the orbit of Mercury, right?
Roughly, yes.
Wow.
It really is the ultimate extreme environment.
It's wild.
It is. Because it is so easy for us down here on Earth to think of a black hole as just, a dark, empty void sitting in the middle of nowhere, quietly vacuuming things up.
Like a giant space drain.
Exactly, like a drain.
Yeah.
But the reality of Sagittarius A, or SGRA as we usually call it, is that the area immediately surrounding it is anything but empty.
Right.
It is essentially a natural laboratory for us. It lets us witness firsthand exactly how matter behaves when it's pushed to the absolute limits of physics.
Right on the doorstep of this thing.
Right on the doorstep, where the gravity is so intense that not even light can escape once it crosses that event horizon. We are watching extreme physics play out in real time.
Okay, let's unpack this. Because for the last 20 years or so, astronomers have been staring into this specific natural laboratory, peering through all the dust and the glare.
And they've been completely baffled by a mystery.
A cosmic whodunit, basically, because they have been watching these very mysterious, highly compact clouds of glowing gas that are actively circling and feeding this supermassive black hole.
Right. Little glowing gas clouds.
And nobody knew where they came from. They were just out there braving the extreme gravity, acting like these perfectly timed appetizers for the black hole.
It's a remarkable detective story, honestly.
It really is. And today we are going to trace the exact origin of these enigmatic gas clouds. We're going back to the scene of the crime to understand the incredible stellar mechanics that are cooking up these celestial meals.
And the challenge here is just monumental. Because, if you are trying to observe the galactic center from Earth, you are looking through 26,000 light years of interstellar dust.
26,000 light years.
Yeah. Dust, debris, intervening gas.
Yeah.
You are not just pointing a backyard telescope at the sky and snapping a clear photograph of what's happening.
Right. You're looking through basically a galactic fog.
A very thick fog. The clues are heavily obscured. The environment itself is incredibly hostile. And the objects we are tracking are, well, on a cosmic scale, vanishingly small.
Elusive little things.
Very elusive. To actually figure out where these specific clouds of gas originated, you have to peel back multiple layers of complex astrophysics.
And use some crazy advanced technology, which we'll get into. But let's start with the victims, or maybe the suspects, depending on how you look at the crime scene.
The G-Cloud family.
The G-Cloud family. Now, looking back at the records, astronomers had noticed anomalies in the center of the galaxy for a while, but things really kicked off with a major discovery back in 2012, right?
That's right. Using some seriously advanced infrared observations, teams spotted these compact gas clouds hanging out uncomfortably close to SGRA.
Uncomfortably close is a good way to put it. And the most famous one, the one that really made the mainstream scientific headlines back then, is called G2.
Yes, G2.
And to give you, the listener, a sense of what we are actually dealing with here, G2 isn't like the size of a star. It contains roughly the mass of 3 Earths.
Which is tiny for an astronomical object.
Minuscule. And the data shows it emits this very specific light signature from hydrogen and helium. which tells us we're dealing with a hot, dusty cloud of gas, not a solid, rocky planet.
Right, and what's fascinating here is that G2 is not just a random, formless fog drifting aimlessly through space.
Like you'd normally picture a gas cloud.
Exactly. When we picture gas in space, we usually think of a nebula, vast, diffuse, very static. But G2 is a highly cohesive, trackable entity. It behaves almost like a solid body in terms of its orders of path. And that path is incredibly elongated or eccentric.
So it's not a nice, clean circle.
Far from it. It moves through this extreme gravitational field, accelerating to thousands of kilometers per second as it swings near the black hole.
Wow.
It acts almost like a glowing tracer die dropped into a rushing river. By watching how G2 moves and how its shape stretches over time, astronomers can map the invisible gravitational currents.
Swirling around the supermassive black hole, that is so cool. But wait, surviving near a black hole isn't exactly a walk in the park.
Not at all.
And this is the part of the data that really made me do a double take. How does a cloud of gas, which is just loosely associated atoms, right?
Essentially, yes. Held together by extremely weak gravity.
Right. So how does it maintain any sort of compact shape when it's subjected to the monumental tidal forces of a supermassive black hole?
It's a great question.
Shouldn't the black hole's gravity just, I don't know, shred it instantly the moment it gets close?
Well, that survival mechanism was the central puzzle for years following the 2012 discovery. Because the tidal forces near SGRA are just beyond immense.
I can't even imagine.
To conceptualize this, imagine you are falling feet first toward a black hole.
Okay, slightly terrifying, but I'm with you.
The gravity pulling on your feet is significantly stronger than the gravity pulling on your head, simply because your feet are physically closer to the center of mass.
Right, makes sense.
So that difference in gravitational pull, that gradient, it stretches you out vertically while simultaneously compressing you horizontally.
Ouch.
In astrophysics, we literally call this process spaghettification.
I always love that term. I mean, it sounds like something out of a cartoon, but it really describes one of the most terrifying ways to be destroyed in the universe.
It is a brilliantly descriptive term. Now, apply that same mechanical stretching to a relatively small cloud of gas like G2.
Okay, so it's getting spaghettified.
Exactly.
Yeah.
As G2 plunges into the deepest part of the gravity well, the front of the cloud is being pulled significantly faster than the back of the cloud.
Right.
According to classical physics, it should smear out entirely into a long, thin, invisible wisp of atoms. It should lose all its structure.
But it doesn't.
Well, it does stretch. Observations show it has this faint, elongated trailing tail that astronomers creatively named G2T.
Ah, G2 tail. Very creative.
Right. But the core of the cloud itself has remained surprisingly, stubbornly compact. It is held together and remained visible much longer than a simple puff of gas should.
That is so weird. And the very fact that we see the bright emission lines of hydrogen and helium means this gas is hot, right?
Extremely hot. It is being energized and ionized by the intense ambient radiation of the environment.
Which is why it glows so brightly in the infrared spectrum even as it's getting stretched out.
Exactly.
Okay, so if I'm picturing this right, it's like a cosmic comet. But instead of a solid rock made of ice and dirt, it's a blob made entirely of glowing hot dust and gas.
Yes, a very hot blob.
Just dragging this faint-tailed G2T behind it as it races at blinding speeds around this massive gravitational sinkhole.
That's a perfect visual.
And just when people were scratching their heads over G2 trying to figure out how it was surviving spaghettification, some researchers went back and mined the old archival data.
Which is often where the best discoveries hide.
Truly. And what they found completely shifted the paradigm. G2 wasn't a lone wolf.
No, it wasn't.
Lurking in the data from years prior, they found an earlier, nearly identical cloud. They retroactively named it G1, and it was traveling on a strikingly similar orbit just further ahead.
Finding G1 was the absolute turning point in this investigation.
Really? Why is that so crucial?
Because the moment you find multiple distinct objects on nearly identical trajectories in astronomy, you have to stop thinking about them as isolated anomalies.
Oh, I see.
A single cloud of gas surviving near a black hole could just be a fluke. Maybe a star that had its outer layers stripped, or a random collision.
Just a weird coincidence.
Right. But two distinct clouds, plus a trailing tail, all following the exact same highly eccentric path through the single most chaotic environment in the galaxy.
That's a pattern.
Exactly. It implies a much larger system. It strongly implies a shared origin or an ongoing mechanism actively producing these objects in a sequence.
Which brings us to the underlying structure connecting them all, because it became clear that these aren't just isolated clumps of gas floating independently in the dark.
The plot thickens significantly here.
It really does. Because recently, observers noticed that gas from G2's tail, that stretched out G2T section, has actually condensed into a third distinct clump.
Yes, another clump formed.
Now, if you are a logical person, you'd assume the astronomical community would name this new clump G3.
You would think so.
But no. When you dig into the literature, you find out they had already used the name G3 for an entirely different, unrelated object somewhere else in the galactic center.
Yeah, astronomical naming conventions can be a bit of a nightmare.
It's a whole separate mystery. We've got telescopes literally called the Extremely Large Telescope, and then we have overlapping designations for gas clouds.
We do our best.
So for the sake of clarity, we'll just refer to it as the third clump. But naming aside, the realization here is profound. G1, G2, and this third clump, they form a streamer.
The G123 streamer.
Right. It's not a set of distinct pearl-like clouds on a string. It's a coherent, continuous, flowing river of material moving straight through the heart of the galactic center.
And that shift from viewing these as individual objects to viewing them as a continuous streamer fundamentally changes how we model the physics of the region.
How so?
Well, when we use words like clumps or clouds, we naturally picture discrete, self-contained objects, perhaps held together by their own internal gravity, like giant gaseous asteroids.
Yeah, that's exactly what I was picturing, little floating blobs.
But the fluid dynamics of this newly identified streamer suggest something entirely different. The gas in this massive cosmic river isn't flowing at a uniform density.
Okay.
It is highly turbulent. It has natural fluctuations and instabilities. As the river flows, sometimes the gas compresses slightly, pushing the atoms closer together.
And sometimes it thins out, I guess.
Exactly, into wider, less dense streams. And the reason we see these distinct visual clumps like G1 and G2, while the rest of the river remains largely invisible to us.
Wait, the rest of it is invisible?
Mostly, yes. And it comes down entirely to the specific physics of how ionized gas emits light in these extreme conditions.
Ah, okay. I want to dig into that physics because it clears up a massive misconception.
Huh.
The brightness of these clouds, the infrared light they shoot at our telescopes, it doesn't increase on a linear scale, right?
No, it doesn't.
The physics dictates that the brightness increases with the square of their density. So if the density of a patch of gas doubles, it doesn't get twice as bright, it gets 4 times as bright.
That's right. It scales with the square.
And if it triples, it gets 9 times as bright. So let me make sure I'm wrapping my head around this. It's not actually a string of separate solid pearls floating in space at all.
Not at all.
It is literally just one continuous river. But because of that squared relationship, the areas where the gas compresses even just a little bit, like rapids in a terrestrial river, suddenly light up like a neon sign.
That is a fantastic way to conceptualize it.
Mm-hmm.
The rapids analogy perfectly captures the fluid dynamics happening on a cosmic scale here.
Well,
we are dealing with continuous flowing matter. When the gas in this stream compresses, maybe due to internal turbulence or subtle gravitational interactions along its path,
the density spikes?
the local density spikes.
Yeah.
And because the emission brightness scales with the square of the density, a section of the river that is just moderately denser than the surrounding flow suddenly crosses a visibility threshold.
So it just pops out of the darkness.
Exactly. It becomes vastly brighter, illuminating that specific compressed knot of gas against the pitch-black background of empty space.
That is wild.
It's largely an optical effect driven by the thermodynamics of the emission process. So, what astronomers have been calling the distinct G clouds for the last decade.
Are really just the rapids.
Yes.
Yeah.
Just the most compressed, highly illuminated rapids in a continuous flowing river of gas that is steadily winding its way towards Sagittarius A.
Okay, so we have this picture now. A glowing, clumpy river of hot plasma flowing relentlessly toward the supermassive black hole.
A majestic, terrifying river.
Truly. But the obvious question, if you are looking at the ecosystem of the galaxy, is what does this river actually do to the black hole itself?
It feeds it.
Right. Because black holes aren't just static sinkholes, they have to eat. They sustain their immense mass by accreting matter. And right here we have a literal river of matter flowing right to its front door.
This river provides the fundamental fuel for the black hole's current state. And what's critical to understand here isn't just the existence of the fuel, but the specific volume and rate of that delivery.
The portion sizes, basically.
Exactly. When the astrophysics teams ran the complex hydrodynamical calculations on this G123 streamer, they calculated the mass of just one of these highly visible glowing clumps.
And what did they find?
We are talking about roughly 1 Earth mass of gaseous material falling down toward the black hole's accretion zone every decade.
Let's put that in perspective, because here is where it gets really mind-bending. 1 Earth mass every 10 years.
It sounds big to us, but...
Right. In the cosmic scheme of things, an Earth mass is practically nothing. The sun alone is over 300,000 times more massive than the Earth.
It's a tiny snack.
A microscopic snack. But imagine taking our entire planet, all the oceans, the mountains, the core, mashing it down into a giant cohesive meatball of hot gas and dropping it straight into a black hole once every decade, like clockwork.
It's a very specific dietary routine.
It's this highly precise, agonizingly slow drip feeding schedule. And what's wild to me looking at the data is that this relatively tiny intermittent meal is exactly what Sagittarius A needs right now.
The precise matching of that supply to the black hole's demand is the key insight here. Sagittarius A is currently what astrophysicists would classify as a remarkably quiet, almost starved supermassive black hole.
Starved? Really?
Yes. If you look deep into the universe at other galaxies, you frequently see quasars. These are supermassive black holes that are actively consuming colossal amounts of entire stars and massive gas clouds at an incredible rate.
Just gorging themselves.
Yeah. Gorging. They generate so much friction, heat, and radiation in their accretion disks that the area immediately surrounding the black hole can outshine all the billions of stars in their host galaxy combined.
That is horrifying, but our black hole isn't doing that.
No, our black hole is doing absolutely nothing of the sort. It is in a low rumble, nearly dormant state.
Okay, so the Earth-sized meatball every 10 years.
That calculated dietary requirement of 1 Earth mass per decade derived from the G clouds perfectly aligns with the current, incredibly quiet energy output of SGRA.
Just enough to keep it ticking.
Exactly. It's just enough material crossing the event horizon to keep the engine simmering, maintaining its low-level X-ray and infrared flickering, but not nearly enough to ignite it into a raging quasar.
So this little river of glowing gas isn't just some random curiosity floating by. It is quite literally the primary life support system keeping our galaxy's central supermassive black hole actively ticking right now.
Yes. Furthermore, identifying this specific streamer solves a massive, long-standing mechanical problem in astrophysics regarding how black holes actually feed in the first place.
Because they don't just suck everything up magically.
Right. The general public often thinks of black holes as cosmic vacuum cleaners that just possess an infinite, inescapable suction, dragging in everything regardless of distance.
Like a giant Hoover in space.
Exactly. But mechanically speaking, getting matter to actually fall into a black hole, crossing the event horizon rather than just orbiting around it endlessly, is incredibly difficult.
Because gravity is a two-way street.
Gravity is a two-way street, and orbital mechanics are stubborn.
Right. It's because of angular momentum. It's the exact same reason the Earth just keeps spinning around the sun year after year instead of plunging into it.
Precisely.
We are being pulled by the sun's gravity, sure, but we are moving too fast sideways. That sideways momentum keeps us locked in a stable orbit. To fall in, we would have to hit the brakes.
That sideways motion is the fundamental barrier to black hole feeding. For matter to fall into the event horizon, it has to lose a massive amount of that sideways motion.
It'd have to shed its angular momentum.
And dissipate its kinetic energy.
Yeah.
Usually in a standard galactic model, this happens via an accretion disk.
Swirling disk of doom we always see in movies.
Right. Gas and dust are drawn toward the black hole, but because of their angular momentum, they settle into a massive, flattened, swirling disk.
Yeah.
Inside that disk, particles constantly rub against each other, creating immense friction.
And friction creates heat.
Exactly. That friction generates heat, and in the process, the matter loses energy. Only as it sheds energy can it slowly, gradually spiral inward.
Like circling a drain very, very slowly.
This process can take millions of years for material at the outer edge of the disk to actually reach the center. But the geometry of the G123 streamer acts as a direct, high-speed delivery system.
Because it's not settling into a nice, polite circular disk. It's diving straight in.
Exactly. The highly elongated, plunging orbit of this specific gas river means the material doesn't have to spend a million years slowly spiraling through a crowded accretion disk.
It gets to ship the line.
Yes. It is already on an extreme trajectory that takes it incredibly close to the black hole at its closest approach, or periapsis.
Wow.
It dives in so steeply that it allows the extreme tidal forces of the black hole to physically strip the material away from the main stream and feed it directly into the inner accretion zone.
So understanding this specific, highly efficient fuel source is truly the golden ticket to understanding the current quiet state of our galaxy's heart.
It absolutely is.
Okay, so we know the meal, it's this clumpy river of glowing hydrogen and helium, and we know exactly who's eating it. Sagittarius A, quietly munching on an Earth-sized gaseous snack every decade.
Just to keep the lights on.
Right, but who is cooking the meal? Where did this massive, perfectly timed river of gas actually come from in the first place?
That is the ultimate question.
Because as we've established, gas in the galactic center gets shredded. You don't just get a continuous, highly structured river of hot gas materializing out of nowhere.
No, you go.
Something massive, something with incredible energy, had to generate it and push it out onto this specific plunging orbit.
And this is where the sheer detective work of modern astronomy comes into play. Astronomers couldn't just guess. They had to formulate hypotheses and examine a lineup of initial suspects.
Let's hear the lineup.
In an environment as densely packed and violently energetic as the galactic center, there are a few usual culprits responsible for generating loose, fast-moving gas. The first suspect on the list was stellar winds from massive stars.
Okay, massive stars, blowing wind.
Massive stars, particularly O-type stars or Wolf-Rayet stars, are incredibly hot, volatile, and luminous. Because they burn so hot, the radiation pressure pushing outward from their cores frequently overcomes their own gravity.
So they just sort of fall apart outward.
Basically, they constantly blow off their outer layers into space at thousands of kilometers per second.
Right, so you have these giant stars just constantly sweating off massive amounts of gas in all directions, flooding the area. That's suspect number one.
The second major suspect was an explosive event, specifically something like a nova.
An explosion.
A nova occurs in a binary system where a white dwarf star slowly siphons matter off a companion star. When enough hydrogen accumulates on the incredibly dense surface of the white dwarf, the pressure and temperature reach a critical point.
And boom.
And it triggers a runaway thermonuclear explosion. This explosion doesn't destroy the star, but it blasts a distinct spherical shell of gas violently outward into the surrounding space.
So suspect number two is basically a colossal, recurring nuclear bomb throwing off shrapnel in the form of gas.
That's one way to put it, yes. And the third suspect was tidal stripping.
What's that?
This would be a much more localized scenario where a perfectly normal, stable star just happened to wander slightly too close to SGR-A on its orbit.
Wrong place, wrong time.
Exactly. The black hole's immense gravity wouldn't swallow the star whole immediately, but it would literally rip the outer gaseous envelopes right off the star's surface.
So it basically mugs the star for its gas.
Yes, creating a trailing stream of material that would follow the star's path.
Okay, so you have three very different, very plausible suspects. A massive star just blowing aggressively in the wind, a star exploding in a thermonuclear blast, or an unlucky star getting mugged for its outer layers by the supermassive black hole.
Correct.
If you are an astronomer, how do you even begin to figure out which one is the actual culprit? I mean, we talked earlier about the 26,000 light years of thick galactic dust sitting between Earth and the galactic center.
It's a huge problem.
If I look towards Sagittarius with a normal telescope, I just see a dark patch of nothing because the dust blocks all the visible light. How do you isolate the clues when you can't even see the crime scene with standard optics?
The dust is the ultimate barrier. Visible light, the kind our eyes see, gets scattered and absorbed by the interstellar dust particles long before it reaches Earth.
So you have to use a different kind of light.
Exactly. To pierce that 26,000 light-year veil of dust, astronomers cannot rely on visible light. They must observe in the infrared spectrum.
Because infrared has longer wavelengths?
Yes, infrared light has longer wavelengths than visible light, allowing it to literally slip past the microscopic dust grains and travel all the way across the galaxy to our telescopes.
That is so convenient.
But simply using an infrared camera isn't enough when you are trying to track something as small as an Earth-mass cloud of gas. You need highly specialized instruments that can not only see the infrared light, but measure the exact minute movements of the gas emitting it.
Right, tracking it.
The international team that finally cracked this case relied on two specific, incredibly sophisticated instruments called Symphony and Iris, mounted on the Very Large Telescope in Chile.
But wait, infrared alone doesn't give you a perfectly sharp image, right? Because even if the light makes it through the galactic dust, it still has to get through our own planet's atmosphere before it hits the telescope mirror in Chile. And our atmosphere is a total mess.
That is the secondary and arguably more difficult challenge. Even if you collect pristine infrared light from the center of the galaxy, the moment it enters the Earth's atmosphere, it gets distorted.
Right.
The atmosphere is constantly moving, churning with different temperatures and densities. That turbulent air acts like a funhouse mirror, bending the incoming light waves.
Which is why stars twinkle.
That is the exact reason why stars appear to twinkle to the naked eye. But in deep space astronomy, that twinkling violently blurs the image, turning a precise point of light into a smeared, unusable blob.
So how do Symphony and Iris fix that?
To solve this, they are equipped with one of the most important technological leaps in modern astronomy: adaptive optics.
Adaptive optics. I've read about this, and it honestly sounds like science fiction.
It really does.
Instead of just building a bigger, static mirror, they build a mirror that constantly changes its own shape to fight the atmosphere.
It is a phenomenal feat of engineering. A system utilizing adaptive optics often shoots a powerful, precisely calibrated laser beam straight up into the night sky.
A laser beam, like a sci-fi movie.
Yes. That laser hits the sodium layer high in the upper atmosphere and causes it to glow, creating an artificial guide star right next to the object the telescope is trying to observe.
Wow, okay.
Because the telescope system knows exactly what that artificial laser star should look like, a computer analyzes how the atmosphere is currently blurring and distorting it.
So it measures the distortion in real time.
The computer runs these calculations hundreds of times a second and then sends signals to a secondary, paper-thin, deformable mirror inside the telescope.
And it actually bends the mirror.
Yes. Tiny actuators behind that mirror physically push and pull its surface, warping it in real time to perfectly cancel out the atmospheric distortion.
That is unbelievable.
It essentially removes the Earth's atmosphere from the equation entirely, giving ground-based telescopes a level of sharpness and resolution that rivals or sometimes even exceeds space telescopes like Hubble.
Okay, so just to recap the sheer amount of technology involved here, they are using infrared sensors to slice through 26,000 light years of thick galactic dust.
Right?
And then they are shooting lasers into the sky to physically warp a mirror hundreds of times a second to cancel out the Earth's atmosphere.
It's quite the setup.
They finally have a crystal clear, magically sharp view of the galactic center. But what are Symphony and Iris actually doing with that clear view? Because they aren't just taking a nice Polaroid picture of the gas clouds.
No.
They are spectrographs. They are breaking the light down.
Spectroscopy is arguably the most powerful tool an astronomer has. It is the science of capturing light and breaking it down into its component colors or specific wavelengths.
Like a prism breaks white light into a rainbow.
Exactly like that. The reason this is so vital is that different chemical elements, when they are heated and energized, don't just glow a generic color. They emit light at very specific, mathematically precise signature wavelengths.
It's like a barcode.
It is exactly like a chemical fingerprint. If you can see the fingerprint, you know exactly what element is present. For this particular investigation, the team programmed Symphony and Iris to focus specifically on something called the hydrogen bracket gamma emission line.
Okay, let's slow down and really explain that, because hydrogen bracket gamma emission line sounds incredibly intimidating.
It's a mouthful.
We established that the G clouds are mostly made of hydrogen. What is the specific line, and why is it the key to tracking them?
To understand the bracket gamma line, we have to zoom all the way down to the quantum level of a single hydrogen atom.
Okay, shrinking down.
A hydrogen atom consists of one proton in the center and one electron orbiting it. Now, that electron can't just orbit wherever it wants. It is restricted to very specific fixed energy levels, or shells.
Like rungs on a ladder.
Good analogy. When the hydrogen atom is sitting in a calm, cold environment, the electron stays in its lowest energy level, the ground state. But the environment near Sagittarius A is anything but calm.
Right, it's a cosmic mosh pit.
It is flooded with intense high-energy ultraviolet radiation from surrounding stars. When that radiation hits a hydrogen atom in the G cloud, it transfers energy to the electron, bumping it up to a much higher energy level. Let's say it bumps it all the way up to the 7th energy level.
But electrons are inherently lazy, right? They don't like being highly energized. They want to drop back down to where they started.
Exactly. The excited state is unstable. Almost immediately, that electron will drop back down to a lower energy level. But energy cannot be destroyed. It has to go somewhere.
So it spits it out.
So as the electron drops, the atom releases that exact packet of excess energy in the form of a photon, a single particle of light. And here is the crucial mechanism. When an electron in a hydrogen atom drops specifically from the 7th energy level down to the 4th energy level.
Okay, 7 to 4.
The photon it releases has an exact, unchanging wavelength of 2.166 microns. That specific wavelength of infrared light is what we call the bracket gamma line.
So by tuning these massive adaptive optics-enabled telescopes in Chile to ignore all the chaotic, blinding light of the millions of stars in the galactic center.
Right, filtering all that out.
And looking only for that one hyper-specific 2.166 micron shade of infrared light, they can essentially put on night vision goggles that only highlight hot, energized hydrogen gas.
That's exactly what they're doing.
They can see exactly where the G clouds are against the darkness.
They can see exactly where it is, but more importantly, spectroscopy allows them to see exactly how fast it is moving toward or away from us.
Oh, because of the movement of the light?
This is the crucial leap that turns a static picture into a three-dimensional moving map. It relies on the Doppler effect.
Ah, like the ambulance siren.
Yes. The same physical phenomenon that makes an ambulance siren pitch higher as it drives toward you and pitch lower as it drives away applies to light waves.
Okay, so how does that work with the gas clouds?
If a clump of hydrogen gas in the streamer is moving physically closer to Earth as it orbits the black hole, the light waves it emits get slightly compressed.
So they squish together.
Yes, that 2.166 micron bracket gamma line gets squished to a slightly shorter wavelength, shifting it toward the blue end of the spectrum.
A blue shift.
Conversely, if the gas is moving away from us, the light wave stretches, shifting to a slightly longer wavelength toward the red end of the spectrum, a red shift.
So by carefully measuring those minute microscopic shifts in the wavelength, what astronomers call radial velocity, right?
Exactly.
And combining that with the exact physical position of the gas on the sky over several years of observation, they aren't just taking a picture. They are mathematically reconstructing the exact three-dimensional speed and trajectory of every single glowing clump in that river.
It is incredibly precise work.
It's like hitting rewind on a cosmic videotape. They didn't just see a cloud of gas, they mapped exactly where it was going, and most importantly for our mystery, exactly where it came from.
And when they finally took all that data and plotted the complete 3D orbits of G1, G2, and the newly discovered third clump over time, the math revealed something profound.
What did the math show them?
When they overlaid the calculated orbits of all three clumps, they found that they all travel on paths with almost identical orientations, eccentricities, and inclinations.
Wow.
This raises an important question. What are the actual odds of that happening completely by chance?
Probably pretty low.
You have to consider the environment. The galactic center is a chaotic, turbulent mess, swarming with millions of stars, competing gravitational pulls, random gas clouds, and intense radiation pressure.
Right, things are just bouncing everywhere.
The mathematical probability of three distinct, entirely unrelated gas clouds randomly falling into the exact same, highly specific, deeply plunging, elongated orbit around the black hole is vanishingly small. It borders on statistical impossibility.
It's like finding three different people from three entirely different countries who somehow ended up walking the exact same convoluted path through Times Square on New Year's Eve down to the exact footstep, completely by coincidence.
Yes, a very good analogy.
It just doesn't happen in a chaotic system.
The data proved beyond a reasonable shadow of a doubt that these were not unrelated phenomena. The shared orbital parameters were the definitive smoking gun.
So they are connected.
They must share a single, localized point of origin. Finding the shared orbit is what transformed these isolated sightings of G1 and G2 from mere curiosities into a connected, trackable timeline of events.
So the detectives have their clues. They have the chemical footprint, the hot ionized hydrogen glowing at 2.166 microns. They have the orbital footprint, this incredibly specific plunging path that bypasses the normal accretion disk and goes straight toward the black hole.
Check.
And they have the speed. So they take all this incredibly precise, massive amount of data gathered by Sinfona and the Iris, they plug it into their computers, and they hit the cosmic rewind button.
Racing the entire G123 streamer backward through space and time.
Following the river up to its source. And the trail lands squarely on one specific suspect from our lineup. They finally unmasked the culprit.
Yes. The culmination of all this tracking was incredibly precise, by mathematically following the trajectory of the streamer backward, both in its physical spatial position and its radial velocity.
Where did it lead?
The path points directly back to a very specific massive star system. This system is located in what astronomers call the clockwise disk, a distinct rotating disk of massive young stars that orbit SGR-A at a distance of about 1/10 of a parsec.
1/10 of a parsec, so pretty close.
Very close in galactic terms.
Ah.
And the specific star system the streamer points to is called IRS-16SW.
IRS-16SW. I've always thought it sounds like a tax form, or maybe an obscure radio station.
It does lack a certain poetry.
It really does, but it's actually something so much cooler and so much more violently energetic than just a single normal star. It's a contact binary star.
A very extreme type of system.
Let's really break that concept down, because this specific type of star system is the physical engine driving the whole operation. What exactly makes a contact binary so different from the stars we are used to?
To understand the extreme nature of IRS-16SW, we have to look at how stars live. Most stars, like our own sun, are solitary objects, comfortably dominating their local solar system.
Right, just hanging out alone.
But a huge percentage of stars in the universe are actually born in pairs, orbiting a common center of gravity. These are binary systems.
Okay, two stars orbiting each other.
In a typical binary system, there is a comfortable vast distance between the two stars. They orbit each other calmly over years or centuries. But IRS-16SW is an extreme, highly evolved case.
They are not keeping their distance.
Not at all. It consists of two incredibly massive, fiercely hot stars that are orbiting each other so closely that their outer atmospheres, their stellar envelopes, are practically touching.
Like their atmospheres are touching.
Yes, they are locked in this incredibly tight, incredibly fast, and incredibly violent gravitational embrace. The orbital period is so short and the proximity so close that the stars are physically distorting each other's shapes into teardrops due to the mutual gravitational pull.
Teardrop-shaped stars. That is so bizarre to think about. And because they are massive stars, they aren't just sitting there quietly, calmly glowing, right?
Definitely not.
We mentioned earlier in our suspect lineup that massive stars have intense stellar winds. A star like our sun has a solar wind. It pushes out a steady stream of particles, which causes the auroras here on Earth.
Right, a relatively gentle breeze.
But the stellar winds coming off massive stars like those in IRS-16SW are on a completely different magnitude. They are constantly blowing a literal hurricane of hot plasma and gas off their surfaces at millions of miles an hour.
Millions.
So if you have two of these giant volatile stars practically rubbing against each other, both pushing out these colossal winds.
The resulting fluid dynamics are explosively complex.
Yeah.
The researchers didn't just assume this would create gas clouds. They ran highly sophisticated 3D hydrodynamical computer simulations to model exactly what would happen to the gas in this very specific scenario.
And what happens when two stellar hurricanes hit each other?
When you have two massive stars in a contact binary, both actively projecting intense stellar winds outward at thousands of kilometers per second, those winds don't just pass through each other.
They crash.
They violently collide in the extremely narrow space between the two stars.
Okay, I have an analogy for this to try and bring these massive astrophysical fluid dynamics down to Earth.
I love your analogies. Go for it.
Imagine you take two industrial-strength gas-powered leaf blowers. You strap them to a table, point the nozzles directly at each other with maybe an inch of space between them, and turn them both on to maximum power.
That sounds dangerous.
Very dangerous. The air rushing out of both nozzles is incredibly fast, but right in the middle, in that 1-inch gap where those two high-speed air streams crash head-on into each other, the air suddenly has nowhere to go.
It's trapped.
It can't move forward and it can't go backward. It violently crashes, it compresses, and it forms this incredibly dense, turbulent, high-pressure knot of air right in the center. And eventually, the pressure in that central knot gets so overwhelmingly high that chunks of that compressed air just have to escape the trap. They get violently pushed out the sides, blowing away as dense, cohesive bursts.
That is an exceptionally accurate visualization of the shock physics at play here.
Really? The leaf blowers work?
Absolutely. When those stellar winds collide in the space between the stars of IRS-16SW, the kinetic energy of the collision has to go somewhere. It creates a massive standing shock wave.
Wow.
The high-pressure knot created by this collision compresses the gas to a tremendous degree, And here is where it elegantly ties back to the optical physics we discussed earlier regarding the glowing clumps.
Just squared brightness thing.
Exactly. That violent collision compresses the local gas so much that it crosses the crucial density threshold required to dramatically increase its emission brightness. It becomes dense enough and hot enough to glow brilliantly in the infrared spectrum.
So the leaf blowers, the colliding stellar winds, are actually manufacturing the glowing clumps in the river. The binary star is literally a clump factory.
Precisely. The shockwave heavily compresses the gas. As this compressed material builds up in the collision zone, it becomes hydrodynamically unstable.
It gets pushed out the sides.
Eventually, that dense pocket of gas detaches from the binary star system entirely as an individual, highly cohesive clump, rather than just a diffuse spray of atoms.
And then it's free.
Once that dense clump is pushed outward and escapes the immediate, localized gravitational grip of the two orbiting stars, it enters the wider environment of the galactic center.
Where the big boss tucks over.
Immediately, it gets caught in the overwhelming, overarching gravitational pull of Sagittarius A. It gets yanked into that highly eccentric, plunging orbit we tracked earlier, beginning its long inward journey and officially joining the continuous flow of the G123 streamer.
That is incredible. But wait, if I put on my skeptical hat for a second and look at the data.
Go ahead.
If all these clumps, G1, G2, and the third clump, are all being manufactured by and ejected from the exact same binary star system, IRS-16SW, why aren't they on the exact same orbit?
That's a very fair question.
You mentioned earlier that their orbits have almost identical orientations, and that was enough to prove a connection, but there are small measurable differences in their paths. G1's orbit isn't perfectly flush with G2's.
No, it's not.
Doesn't that discrepancy throw a wrench in the entire theory? If they come from the exact same gun, shouldn't they follow the exact same bullet trajectory?
On a static, stationary system, yes, they would. But pointing out those slight orbital differences actually strengthens the theory beautifully because it proves the dynamic nature of the source.
How so?
Think about the physical reality of IRS-16SW. It is a binary system, meaning those two massive stars are constantly rapidly revolving around each other. But beyond that, the entire binary system itself, the whole package, is actively orbiting around the supermassive black hole as part of that clockwise disk of stars.
Yeah, it's moving.
It is a moving, rotating, spinning platform in space. So when the colliding stellar winds build up enough pressure and eject a clump of gas, say the clump that became G1, the binary star, is located in one highly specific position in its orbit around the black hole, facing one specific direction and moving at a specific velocity.
Ah, I get it. It's like throwing a baseball out the window of a moving car. The speed and direction of the car entirely affect the final trajectory of the ball.
Exactly. The initial vector of the gas clump is a combination of the ejection force and the underlying movement of the star system itself.
Right.
Now, fast forward 10 or 20 years to when the collision zone builds up enough pressure to eject the next major clump, G2.
The car has driven further down the road.
Exactly. In that intervening time, the binary star system, IRS-16SW, has physically moved further along its own massive orbit around the black hole. It is in a different spatial location.
So the angles change.
The angles of ejection have changed slightly relative to the black hole. The rotational phase of the binary stars themselves might be slightly different at the exact moment of ejection.
That makes perfect sense.
Therefore, the resulting orbital path of G2 will be profoundly similar to G1 because it originated from the same core gravitational zone, but it will inevitably have minute, mathematically predictable differences.
Caused by the simple fact that the clump factory itself is spinning and moving through space over time.
Precisely. When astrophysicists modeled the ejection of material from a moving orbit matching IRS-16SW, the slight, documented differences in the orbits of G1, G2, and the third clump perfectly matched the modeled orbital dynamics of a moving source.
That is just, it's incredibly satisfying when the physics puzzle pieces fit together that perfectly.
That's what every scientist lives for.
You have the fluid dynamics of the colliding winds perfectly explaining why the gas is hot, compressed, and clumpy enough to glow brightly in the infrared.
Yeah.
You have the macro movement of the binary star system perfectly explaining this slight measurable variations in the orbital paths of the distinct clumps over decades. And you have the overall overarching gravitational trajectory pointing right down the barrel, delivering this material straight to Sagittarius A. It leaves absolutely no room for doubt.
It truly is a triumph of modern astronomy. It demonstrates how observational data-gathering photons that have traveled for 26,000 years and theoretical hydrodynamical modeling can work perfectly in tandem to solve a complex multivariable mystery in an environment we can never physically visit.
So after taking this hour to really dig into the mechanics of this, what does this all mean for our understanding of the universe?
It's a huge paradigm shift.
When we step back from the specific infrared data points and the orbital math and look at this whole story, we've clearly moved past just solving a niche mystery about some glowing gas clouds puzzling a few astronomers.
We have uncovered an entire ecosystem.
A majestic and frankly terrifying ecosystem operating continuously at the center of our galaxy. It fundamentally changes the narrative. It's not just a story about a dark, dormant black hole arbitrarily, passively eating whatever unlucky material happens to wander too close.
Far from it.
It is a highly structured, perfectly balanced, mechanically driven cycle. You have this chaotic, dense disk of material swirling around the black hole where massive volatile stars are born.
Yes, the clockwise disk.
These stars live incredibly fierce, short lives and frequently pair up as these extreme violent contact binaries like IRS-16SW. Their violent lives and constantly colliding winds act as a mechanical factory,
Churning out these dense, compressed clouds of hot plasma.
and those clouds inevitably get pulled inward by the massive gravity gradient, stretching out and forming this glowing, structured river that bypasses the slow accretion disk and delivers a slow, steady, highly efficient drip of fuel directly to the supermassive black hole.
The black hole that anchors and dictates the gravity of the entire system.
It's not a random feeding, it is a continuous, self-sustaining, deeply connected loop.
And if we connect this localized discovery to the much broader, overarching picture of astrophysics and cosmology, the implications are profound.
How so?
For decades, the scientific community has tended to study different fields of astronomy in somewhat isolated silos, out of sheer necessity due to their complexity.
Because there's just too much to know.
Right. We have the field of stellar evolution, which focuses entirely on how individual stars are born from nebulas, how they live, how they burn their fuel, and how they eventually die.
Okay, that's a one silo.
We have the field of interstellar gas dynamics, which relies on heavy fluid mathematics to model how plasmas and atomic clouds move, shock, and cool through the vacuum of space.
Silo number 2.
And then we have the entirely separate study of active galactic nuclei and black hole feeding mechanisms, which tries to understand how the dark, incredibly massive cores of galaxies grow, emit radiation, and evolve over billions of years.
And what you were saying is that this single discovery in our own galactic center just grabs all 3 of those massive, historically separate fields of study and ties them tightly into a single, undeniable knot.
Precisely. It elegantly, visibly proves that these cosmic processes are not isolated phenomena happening independently of one another. Stellar evolution, gas dynamics, and black hole feeding are intimately, mechanically, and crucially linked.
They're all part of the same machine.
The life cycle of the stars residing in the galactic center directly dictates the feeding habits, the energy output, and ultimately the growth rate of the supermassive black hole.
Wow.
The violent death and volatility of matter happening on the relatively small stellar scale acts as the direct fuel source for the gravitational giant operating on the massive galactic scale.
It scales all the way up.
By observing the G123 streamer and its source, IRS-16SW, we are seeing right here in our own Milky Way a highly localized, perfectly observable version of the exact physical processes that likely shape the evolution, growth, and radiation output of entire galaxies across the entire observable universe.
That is just staggering.
It proves that even in an environment as violently chaotic, dense, and seemingly random as the center of a galaxy, there is an underlying beautiful mechanical order to how mass is transferred, compressed, and ultimately consumed.
It really is breathtaking when you take a moment to internalize the sheer scale and the mechanical perfection of it all.
It is a beautiful machine.
To briefly recap this incredible journey for you listening, it all started with a mysterious, faint, glowing clump, G2, spotted through the interstellar dust, braving the seemingly insurmountable spaghettification forces of a supermassive black hole back in 2012.
And that single anomaly sparked everything.
That initial anomaly led to a decade of data mining and the profound realization that G2, along with the earlier clump G1 and a newly formed third clump, weren't isolated random clouds at all,
but highly compressed illuminated rapids in a continuous flowing cosmic river of hot plasma.
diving straight towards Sagittarius A. By pushing technology to its absolute limit, utilizing mind-bending adaptive optics to cancel out our own atmosphere, and highly sensitive spectrographs to track the exact Doppler-shifted infrared signature of hot hydrogen.
Astronomers were able to trace that fast-moving river backward through 26,000 light-years of incredibly hostile space.
And they found the definitive source. A pair of massive stars locked in a violent, high-speed orbital embrace, violently crashing their stellar winds together like cosmic leaf blowers,
creating dense, glowing knots of gas that break off and feed our sleeping giant of a black hole one precise, Earth-sized meal every 10 years.
It is a remarkable testament to human curiosity, the scientific method and breathtaking technological advancement that we, sitting on a small, rocky planet on the edge of the galaxy, can piece together such a complex, invisible narrative taking place in the most extreme, highly obscured environment imaginable.
It really is one of the greatest detective stories ever told.
It absolutely is. But as with any good story, wrapping up this mystery just opens the door to another one.
Always. There's always another mystery.
It leaves me with a final, lingering question to ponder as we wrap up today. We established that massive stars, like the ones in IRS 16SW, live incredibly volatile, furious lives.
Yes. Very short, very furious lives.
Because they burn so hot and blow off so much mass, they burn through their nuclear fuel incredibly quickly compared to smaller, calmer stars like our sun. They might only live for a few million years.
A blink of an eye in cosmic terms.
So if this one specific contact binary star system is essentially operating as a slow drip IV, solely responsible for keeping Sagittarius A fed and ticking right now, what happens to the center of our galaxy when that specific star system inevitably runs out of fuel and dies in a supernova?
That is the million-dollar question.
Will that continuous river of gas dry up? Will our supermassive black hole finally go entirely hungry, its accretion disk emptying out, falling completely, utterly dormant and dark? Or is the dense, dusty heart of the Milky Way secretly filled with a whole hidden ecosystem of unseen, tightly wound leaf blower binary stars, just waiting in the wings to take its place and keep the cosmic engine running?